All right, so we've been talking about chromatic polynomials. So to remind ourselves, the definition of chromatic polynomial, it's going to be some polynomial in terms of k. K always has to be an integer. And the actual formula from the chromatic polynomial, if you plugged in some number for k, would give you the number of k colorings that exist in your graph. Symbolically speaking, I'll use the same one right here that is in your book, which is capital P subscript variable k, and inside of parentheses, the name of your graph. But it's also pretty common to see those two things reversed inside the parentheses, which is often where you see functions and their variables, and then down here as part of the name of your polynomial, the name of the graph. Again, both of them perfectly fine, but this is the naming convention I'll stick with. And I was actually looking up some stuff the other day. Oh, it was probably actually just yesterday. And on one of the places online, instead of using p, they actually used pi instead of p for the chromatic polynomial. And I was looking at that, and I was just like, that's not super common, but okay. So there's lots of different ways that you can see it, but it's normally p or pi. All right. So in terms of our inequalities here, we talked about this inequality previously. We said that realistically, in terms of the k colorings that exist in your graph, realistically speaking, this integer k would vary somewhere between your chromatic number, which remember your chromatic number was the fewest number of colors possible that you could use and get a coloring in your graph, all the way up to the total number of vertices where you colored each of your vertices of your graph a different color. Okay? Now, in terms of the polynomial, people don't always specify that range. Sometimes they just say k in general, and then from the k, that could be any integer, you're actually able to recover these numbers right here. Okay? And we started to see that a little bit last time. No, it looks like this thing is stuck. Don't be stuck on me. It's okay. Come on, we can scroll. It does this sometimes. We've all seen it happen before. There we go. All right. So last time we had one example of creating our chromatic polynomial, and one of the things that we talked about after class when many of you had already left, but I wanted to share it because it's actually something that's really critical. This particular method that we did last time, where we said, hey, we've got this path. The first vertex in the path could be colored with any of our k colors. So k here was the number of colors that we were assuming that we could potentially use. You could use any k colors in the first one. The second vertex that we looked at, then the only color you weren't allowed to use was the one that was adjacent to that vertex B. Then when we looked at vertex C, the only color we weren't allowed to use was the color that was adjacent to vertex C, so the blue. And D, the only color we weren't allowed to use was the color that was adjacent to D, so the yellow from vertex C. And then with E, the only color we were not allowed to use was this purple that was the vertex adjacent to E. This strategy does not work on all graphs, and in fact, it works on very, very few graphs. It does, however, give you an idea of a way to build your chromatic polynomial with very, very specific types of graphs. The specific types of graphs where this can be used is exactly 3. Okay? 1, path graphs, and you can do it exactly like what we did right here. 2, trees. Yes, so remember, k here doesn't have to be dealing with the coloring that's the fewest number of colors. So if k equals your chromatic polynomial, that's when you could, in this case, be 2 because the chromatic number for this graph is actually 2. Okay, so you're totally correct. You could totally have just alternated between the blue and the yellow right here. I on purpose threw in the purple just to illustrate that this strategy works regardless of whether you're down here with the fewest number of colors or if you're up here with a whole lot more colors. Okay, where was I? Right. So you can use this strategy on path graphs. Actually, let me write this to the side. And let me actually color code it so it is hopefully more obvious. Note, how about warning? Warning might be better. Why am I using purple for a warning? What do we use in warning? Some big obnoxious color. Do we have a really large obnoxious color? Not one I normally use. I am not seeing a super obnoxious color. How about orange? That's kind of bright. Warning! All right. That's enough of an obnoxious color. We'll box it too. All right, so back to black. So this method, and this warning is a little bit of a lie. Yeah, but I did red for examples was the only reason I didn't want to do red. So this method works for path graphs. This works for complete graphs. And it works for trees. And technically, we haven't defined trees. We're going to do that today. Okay. You can actually use this method for other types of graphs, but you have to be really, really, really careful, and you have to do a buttload of different cases. So we're not going to go into the specifics of how to use this for other types of graphs, and quite frankly, you really don't want to anyway. Okay, so we're going to have a different strategy for the other types of graphs, and it's going to be something a little bit different. So this strategy right here only works for those three types of graphs. And again, we'll define trees in just a second. Now, before we get into dealing with some of the properties of our chromatic polynomials, I did want to go back and look a little bit more at this guy because we were running out of time right as we started building our chromatic polynomial. Okay, so we ended here and we had our chromatic polynomial. So we said the chromatic polynomial, this guy was just k, the first factor, and then we multiplied all these other options that we labeled our vertices with. So we multiplied by 4 of the k minus 1 guys. Now, remember what you can do with polynomials, and specifically one of the things that you can do with your chromatic polynomials is the use of this guy is to plug in values of k, okay? Now, even though up here in our, what we said k was, even though we said, hey, k can be what? It can be any integer. Realistically, k is not going to be a negative integer. How can you have a negative number of colors? Realistically, you're not going to have 0 colors unless you're the empty graph, the graph that has no vertices. So realistically here, I'm going to go ahead and adjust this. You would put a little plus sign up in what looks like, wow, that's a terrible plus sign. Just a second. Let me actually brace my hand so it's not a crazily drawn little plus sign right there. All right. So here, there's a little plus sign. And you haven't seen that symbol before. This symbol with a little plus sign, this is positive integers. So it's 1, 2, 3. It's all the positive integers. Okay. So that just tells you k, 1, 2, 3, etc. some positive integer. Now, why did I mention that? Because let's go ahead and see what happens if we actually do plug in our potential values of k into our chromatic polynomial that we just found. And I'm going to claim that we're actually going to be able to get a fair amount of information from this guy. Okay, let's scroll back down here. The first thing is what happens if we actually plug in, well, I'm going to go ahead and plug in 0, even though that only works when your graph has no vertices. So if we actually tried to plug in 0 here, what happens? Well, we would get the chromatic polynomial would be 0 times negative 1 to the 4th, or 0. Now, what does this tell us? This 0 right here tells you you cannot color this graph with no colors. It doesn't work. Okay? Then, if you go ahead and plug in k equals 1, what happens? You'd have 1 times 1 minus 1 raised to the 4th, or still 0. Note what that tells you. This tells you this graph, there is no one coloring in this graph. Now, if you guys look at that graph, hopefully you are thinking to yourself, yeah, there is no way that I can actually color that graph with only one color. Why? Because I have edges involved. And as soon as you have edges involved, what happens? You have a 2-click. And that tells you that the smallest your chromatic polynomial could ever be is, your smallest the chromatic number could ever be is 2. Okay? Now, for a path graph, the chromatic number actually equals exactly 2, which is why you can alternate these guys, yellow, blue, all the way down. You can actually do it without 3 colors like we did this 3 coloring up here. You can do it with actually just 2 colors. Okay? And notice down here, that was the thing we did last time. We plugged in k equals 2. We had 2 times 1 to the 4th, or 2, and what this told us was if we actually went ahead and drew out our path graph, 1, 2, 3, 4, and 5, we could totally have just colored this guy with 2 colors, and I'm going to be lazy. Color it with yellow and color it with, we'll go ahead and do the blue since we talked about blue before. Okay. And if there's 2 possibilities, you could have done it in that orientation with 3 yellows and 2 blues, or you could have flip-flopped the yellows and blues and done 3 blues and 2 yellows. Okay. And that's where this 2 right, did not mean to have that do that. So that's where that 2 comes into play. It says, how many possible ways could you create a 2 coloring in this graph? There are 2 of them. Okay. Now what happens if you wanted to use 3 colors? So if K equals 3, what's going on? In this particular case, you plug it in, and you'd have 3 times 3 minus 1 to the 4th. I'm probably going to stop at this one. And what would we have? We would then have 3 times 2 to the 4th. What is that? 16 times 3, or 48 different ways that you could create a 3 coloring. Now, watch out. If you use 3 colors, that's not the fewest number of colors that you could ever use for this particular path graph, but you could still do it. It exists. It's fine. And it turns out that there's 48 different ways that you could actually color that graph with 3 different colors. Okay? So that would be one of the ways that you can use this chromatic polynomial. Notice when we grabbed our chromatic number, what was it? It was the smallest value for K, where when you plug that value for K into your chromatic polynomial, you didn't get back a 0. Okay? So that's actually one of the ways that you can use your chromatic polynomial to go and find your chromatic number. And I have to admit, when I was prepping for class yesterday, when we were talking about chromatic numbers and we hadn't yet gotten to the polynomials, my husband comes in and he goes, well, that's easy. You just use the chromatic polynomial to do blah, 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 blah. And I'm like, yeah, but we haven't done chromatic polynomials yet. We're actually going to have to figure it out. And he goes, I don't want to do that. And he walks away. I was like, that's fine. You don't have to do that. Okay? But this is one of the ways where you can start doing the interplay between chromatic polynomials and chromatic numbers. Now, it turns out that your chromatic polynomial also gives you more things. So I should have enough space to write this more stuff. So the next thing that I want to do is, and the other stuff that we do with our chromatic polynomial, we have to actually have the chromatic polynomial expanded. So let me rewrite this polynomial with just the k's, not plugging in. So we'll have k times k minus 1 raised to the 4th. But now we want to go ahead and expand it. Are you guys okay if I just write it out? I don't know how comfortable you guys are with multiplying out something to an exponent. So I'm going to do it, and if you guys, and then we can talk about it if you guys need to. So if you want to go ahead and expand out k minus 1 to the 4th, this guy is simply k to the 4th minus 4k cubed plus 6k squared minus 4k plus 1. And then so to get the actual expanded version of your chromatic polynomial, this guy would be k to the 5th minus 4 times k to the 4th plus 6k cubed minus 4k squared plus k. Okay. Everybody okay with what I did? And of course, you can always just multiply out the k minus 1 to the 4th as many times as you need to. But this here is that shortcut method. It's typically taught in high school where you're dealing with Pascal's triangle behind the scenes. Okay. If you guys want me to go over it, I will. Otherwise, I'm not seeing any questions where you're having trouble with that, so I'm just going to move on and talk about the pieces and parts that you can see out of this polynomial. Okay. Now, this is a semi-representative polynomial, and you can go ahead and see a lot of information from this. One of the pieces of information to notice here is, notice the degree. So actually, let me highlight the key things here. The degree of the polynomial up here at 5. That degree tells you something, okay? Now, the other thing that's going on here that's going to be important is actually this guy right here. Specifically, notice all of the signs are alternating. It turns out that's an important thing as well. And there's a couple of other important things as well, and we'll go ahead and go over them. One of the things that happens in terms of the standard form that you'll see is you'll see that there's an k minus a number is what your different factors are going to include. So that allows you to, that means that you're always going to have these alternating signs. The k raised to an exponent at the top, that degree, you would have one of these factors of k or k minus 1 or k minus 2 or whatever k factor you have. This guy is going to tell you how many vertices you actually have in your graph. And these other bits and pieces also tell you some things. So we'll come back and identify the pieces and parts in this particular chromatic polynomial here in just a second. But let me actually give you the theorem that deals with all of those specific things. Yes is the answer to that question, and we're going to have an example like that in just a second. All right, so this is a theorem, and I do not know why your textbook actually doesn't include it. It's a really, really useful theorem. When I saw that your textbook didn't have it, I was like, well, that's problematic. So I actually pulled the phrasing of this from a different textbook that I've got. So this one here, the theorem goes as follows. You've got some graph that has V vertices, so V would be the number of vertices. It's got E edges, so E would be the number of edges. And its chromatic polynomial has this format. It's just some polynomial. So you've got P with a subscript K, G is your graph. It's just some sum, and I went ahead and expanded it out. So the first term here is K to the same power. That power right there is the number of vertices, right there. And then it decreases all the way down till you potentially have a constant term, okay? And remember, standard form here, back from almost any time you would have seen this sort of thing with sequence notation. These subscripts are just your coefficients on the k's, okay? So the first thing is the degree of your polynomial is V, and it looks like I need to do a quick switcheroo. This is the same as our V right there, so it's that guy. Okay. Also, the leading coefficient always turns out to be 1. Interesting, but true. Okay. It comes from, the formulas are going to get way more complicated than the chromatic polynomial for a path function, for a path graph, but what you can see here is indicative of what would happen. Notice we just had a bunch of linear terms, so k minus something multiplied together, where k is the same as k minus 0. So notice your leading coefficient is only 1 there. Okay? It also turns out that the very, very last term right here, you're never actually going to get a constant term. Strange but true, but we can actually see that being indicative of up here, your very, very first vertex where you place your first color on that first vertex you choose to put the color on. You could always represent that as a k times something. So what does that mean? That means you always have a factor of k, which means your lowest term or your term with the k with the smallest exponent would be potentially k to the first power or k to the second power, k to the third power, but no constant term. This next one is actually relatively interesting. This one says not your leading term, but the next term down. So that's this guy right here is actually going to give you how many edges are in the graph. So that coefficient on the, not the leading term, but the next term down, number of edges. Now notice this negative here. This is actually saying, hey, if you have a plus symbol here, you'll just flip the sign of whatever you're actually given. Also, coefficients will turn out to always alternate in sign. We saw that up here. It turns out that's true in any chromatic polynomial. Notice what that means, though, for this number of edges. This second term would always really be a subtract something. So whatever number's after the subtraction symbol, that's the number of edges in your graph. Okay? And lastly here, this tells you something about your smallest term or your last term. The smallest n, so the smallest exponent on k that actually is visible in your graph, is equal to the number of components in G. Now, let's pull all this information and see how it reads off of the chromatic polynomial we built when we start off with the graph and see if it actually works with our path graph. According to this, 5 equals the number of vertices in our graph, because 5 was our degree of our polynomial. Second one, the leading coefficient is 1. Check, we've got that. Third thing is we don't have a constant term. Check, we've got that. Third, well, I guess really fourth thing down here says that the coefficient on the k to the fourth term is the number of edges. So this tells us that 4 is the number of edges in the graph. Okay. Down here it says the coefficients alternate in sign. So note this guy B, C, and E. This just tells you properties of what's going to happen in any old chromatic polynomial. It's one of the ways to check if you build a chromatic polynomial, did you actually not make any mistakes? So for example, if you get a constant term, you made a mistake somewhere. If the signs don't alternate, you made a mistake somewhere, type thing. If your leading coefficient isn't 1, you made a mistake somewhere. But in terms of actually pulling information out of the chromatic polynomial, the ones that don't have the bullet points next to them are the ones that give you information. This last one right here tells you the number of components. So you look for your smallest term or your exponent on k that is the smallest. So in our case, it would be this one. So things that we looked at the leading term, we looked at that coefficient, and then we looked at that smallest term. This guy, since the exponent on that k is 1, this tells you the number of components in your graph G, and since the number of components in your graph G is 1, this actually tells you your graph is a connected graph. Okay? So those are some of the big things you can get out of your chromatic polynomial. It's not just finding the chromatic number. It's not just finding how many colorings using a certain number of colors that you can find. You can also get the actual structure of the graph. Now, let's double check that that actually worked for our path graph. Our path graph that had 5 vertices, well, we had 5 vertices. Do we have 4 edges? Well, 1, 2, 3, 4. Yep, we got 4 edges. And number of components, do we only have 1 component? Yep, it's totally a connected graph. So notice this stuff totally matches up with what we had with this example too. Okay? Now, kind of okay so far. I'm crossing my fingers here, although you can't see it. All right, I see no questions yet, which means either you guys are suitably overwhelmed or you're okay so far. So to figure out which is which, let us go now to the next question. So the next question, part of that next question, specifically the first part of that next question, I actually threw to you guys on a poll everywhere question. Okay? So I'm going to go ahead and share the 2 screens, and then we'll stop sharing the poll everywhere question. And I'm doing this on purpose. That way, if you've forgotten what this URL is, or if you came in after the sort of intro screen was when you log in at the beginning, you still have it so you can go and access these poll everywhere things. Okay? So it's the normal place. If you have it on an app, you just go to the one for our class. If you're doing this through an actual internet browser, the URL is up there at the top. So the question here, and I realize that in this screen I'm sharing, it's, oh good, it's almost, all the words are not covered up, good. So the question is, this polynomial in terms of k that's given, so k to the 5th minus 3 times k to the 4th plus 3 times k cubed minus k squared. What we want to know is, does it look like it could actually be a chromatic polynomial for some graph, okay? So that's the first question. I'm going to let you guys take a guess, figure out if you think it can be. If the answer is no, think why it's not possible. If you get an answer of yes, we're going to try to build a graph that actually has that chromatic polynomial. And I am on purpose trying to keep up this theorem here because this theorem tells you when your chromatic polynomials exist, or tells you the specifications you need to have for your chromatic polynomials. And then, of course, my screen froze, so I'll try to fix that screen while you guys are answering this. There we go. All right, it looks like most of you guys got an answer in. So while the last couple of you are throwing in answers, I'm going to go ahead and hide that screen. All right, so let us go over this together now. So while you guys were looking at this, I went ahead and started rewriting the chromatic polynomial, which is not in any way, shape, or form helpful to what you're currently doing. So you, in no way, shape, or form is a factored form of the chromatic polynomial more useful if you're trying to pull information out of it. So notice here in this theorem, if you're trying to use this theorem that is not in your textbook to pull information out about your chromatic polynomial, whether your polynomial actually is a chromatic polynomial or whether you're trying to use the chromatic polynomial of a graph to figure out things about the graph, you actually want it in the expanded form. Okay? I factored for a different reason. It's for something we haven't been asked yet. Okay? So for this guy, if you walk through these things, first thing it says, is your chromatic polynomial supposed to have the same degree as the number of vertices? So the degree of this polynomial is 5. Could we have a graph with 5 vertices? What do you guys think? Yeah. Now, I don't have any graph in front of me, so I don't know if that's actually what we have here, but is it possible to have 5 vertices? Psh, yeah, whatever. So we'll go with it for now. Now, the second component here says this has to be true for all chromatic polynomials. It says, hey, your leading coefficient better be 1. In our polynomial that we were given, was our leading coefficient 1? And hopefully you're all thinking to yourself, yep, we're good there. Okay. So then the next thing we go down and check and we say is, all right, do we have a constant term? So looking at our given polynomial, do we have a constant term? Correct. We don't have any constant term. The lowest exponent we have here is a k-squared term. So we do have the fact that that constant term is a 0. And in fact, if you wanted to use the same notation, we could also say that a1 equals 0. Not required in any way, shape, or form, though. Okay. That takes care of the first 3 things. Fourth thing says that we could figure out the number of edges in this particular graph. It says pull the second coefficient, so leading term, second term. The second term here is -3, which according to that theorem tells you that you should have how many edges? This is telling us that we should actually have 3 edges. Now, do you think that there's a graph out there that exists that has 3 edges? Is it possible to build a graph with 3 edges, in other words? Hopefully you're all thinking yes. Do we know what this graph is? No, but is it possible to have 3 edges? Yes. Now, how could this one fail? Suppose you actually get that A4 was +3, then that would say, if this was +3, that would tell you that the number of edges was supposed to be -3 edges. If you got that the number of edges in your graph was supposed to be -3, that would tell you what? That would tell you that, hey, it can't happen. You can't have a negative number of edges, okay? That's how this one would potentially fail. Now, next part down here is part E. Part E says your coefficients in your polynomial, as long as you write it in either ascending or descending order by the exponents, are supposed to alternate in sign. So quick check, do the coefficients here alternate in sign? Yep, they totally do. So alternate in sign, we're good there. So the only thing we have left to check is this last one here, this part F. So part F says find your smallest term, so your term with the smallest exponent. In our case, this would be this k squared. So this is telling us that the number of components of the graph is supposed to be 2. Is it possible to find a graph that has 2 components? Yeah, there's nothing against having a graph with 2 components. So this is something that is totally possible. Now please note broad strokes. These ones with the bullet points are the broad strokes ones you check first typically. And then these other ones, the only thing you check is, hey, degree, it's got to be at least 0 or 1, typically at least 1. Edges, you want to make sure that your edges are actually a positive number, but if part E is satisfied, D should automatically be satisfied. And this one here, if part C is satisfied, F should automatically work out too. Okay, so realistically, if these 3 guys with bullet points are satisfied, it's highly unlikely that A, D, or F could ever fail. The only issue then of whether it actually is a chromatic polynomial is if you can find a graph that has that number of vertices, edges, and components. Okay, so the issue here in actually is it a chromatic polynomial as opposed to could it be a chromatic polynomial. The could it be a chromatic polynomial is just does it have the right format to be a chromatic polynomial, and then is it a chromatic polynomial? That's when you go and find a graph that actually meets these specifications. Okay, so for this one here, this one we could say, yep, it could possibly be a chromatic polynomial, so I'm just going to write that. It could be because it has the right format. It has the right format. Now, we still have to actually figure out if it really is, and that's when you go and you find, you try to find a graph. Okay? Now, when you try to find the graph, the things that you look for are the non-bullet point parts. So here we're looking at, we need 5 vertices, we need 3 edges, and we need the 2 components. So those are the 3 pieces of information that we are going to care about. And yes, you got it for the last person who put in the description there. So there are 2 main graphs that I thought of for this. And let me put down one of them. Both of them meet the description that you guys wrote down there. So here's my claim. Now I'm going to go ahead and box this guy just because it's a disconnected graph. And I have to admit, when I write down disconnected graphs, my brain always jumps to connected graphs. And I'm like, oh, I have 2 graphs here. No, no, no. Remember, disconnected graphs look like multiple connected graphs. They're just sort of hanging out in the same region. So let's check to see if this works. So we had 1, 2, 3 vertices plus 2 more. So there's our 5 vertices. Let's check to see if that has the 3 edges. So 1, 2, 3 edges. Okay, so that works so far. And we have 2 components. Check. So this here would match exactly with what we're supposed to get pulling from this chromatic polynomial. Now, here's the last step. Let's make sure that this actually gives us the correct chromatic polynomial, and this is why I was starting to factor our chromatic polynomial. Okay? Now this guy inside of parentheses is actually a really, really common polynomial. So I'm just going to go ahead and give you the factorization. Again, if you guys want to know how to do those polynomial manipulations quickly, I'm happy to tell you, but unless you guys ask, I'm just going to assume you're okay. So that last part, that k cubed minus 3k squared plus 3k minus 1, that is actually the expanded form of k minus 1 cubed. Okay. Now, let's go down and build the chromatic polynomial for the disconnected graph that's boxed in that dotted line there at the bottom. And notice here, both of those are teeny, yes, all right. So let me go ahead and finish building the chromatic polynomial for the box graph, and then I'll show you the tricks for the polynomials. So here, notice there are 2 little baby paths. So we could actually build the chromatic polynomial for this guy the same way we built the chromatic polynomial for the previous example that was a 5-vertex path. Okay. So what do? I'm going to go left to right. So on this top one, number of colors that you could use in the very first vertex. You could use any of the colors in play. And remember, K equals the number of colors that you're currently using. Then you can only deal with a vertex that is adjacent to a colored vertex. So we can assume that this guy is colored. So how many possible colors are in play for this vertex that's adjacent to that other vertex we just dealt with? Well, it would be K minus 1. And what about the third vertex on that top piece, or this top component? How many colors are now in play for that last guy? It would also be K minus 1 again, because for this last guy, we could actually use the color that was used originally 2 vertices back, so it's still the same K minus 1. Now, here's the different part with disconnected graphs, and we'll have this official rule with disconnected graphs or property of disconnected graphs in just a second. But what you do with disconnected graphs is you just build a chromatic polynomial for each piece, and then we'll multiply them all together. So for the 2 vertex path, how many potential colors could you color that very first vertex on the left? Okay, now what about the 1 remaining vertex? K minus 1. So when we put this all together, our chromatic polynomial right here would be K, so on the first piece, K times K minus 1 squared. And then on the second piece, that would be K times K minus 1. And if you put the chromatic polynomial all together, I'm just going to combine the factors. This would be K squared times K minus 1. Okay. Now, is that the same as our given chromatic polynomial? Yeah, it is. And that's why I was going back and factoring the given polynomial, because the given chromatic polynomial, it was definitely more useful to us when we were given the chromatic polynomial at the beginning of this question to have it in that expanded standard polynomial form. But the factored form was useful when we started looking at and checking to see if this graph we created had the same polynomials up top. Okay. It turns out there is another way of having another graph with the same chromatic polynomial. Anybody have a guess on what we might do for a second graph with the same chromatic polynomial? This one's trickier to see. Yeah, you got it. Good job, guys. Here would be like you have a start graph. Make sure I get them all in there. Somebody like this, and then one little vertex. Oops, I wanted to do a dotted line. One little vertex that's all by himself. Those little vertices that are all by themselves are called isolated points or singletons. Singletons is actually the proper word. The description that people use those isolated. Okay. Or atoms, they're sometimes called that too. As in, like, you can't get any smaller than an atom. All right, so if we look at this guy, these are fundamentally different than the paths that we've done before. Okay? So I'm going to look at the vertex first, because the one single vertex, the singleton right here, is actually like a path that has no edges. So if we looked at this guy that's all by himself, any guesses how many of our K colors we could use to color that vertex that's all by himself? Yeah, you could use any of them you want. It doesn't matter, so K. Now, the one that actually takes a little bit of work is this guy next to him that's instead of a path is a star. I personally like to start at the vertex in the middle that's degree 3, but you do not have to. You actually could start at any of these outer degree 1 vertices as well. So do you guys have a preference? Do you want to look at the degree 3 vertex first or one of the degree 1 vertices? It won't matter. All right, the only votes I have in are, looks like for the middle one, so I'm guessing you meant degree 3. So if we look at this very first vertex right here, how many different possible colors could we color that first vertex? Yeah, you could do any of our K colors. Now, when we go out to our degree 1 vertices, so maybe we do the top one first, so go straight up. How many colors could we color that degree 1 vertex that's straight above the middle one? You could do K minus 1. And notice, that's like building a mini itty-bitty path. Now, there's nobody else above, so we'll come back down. And if we go maybe, say, to the right, so this vertex here is adjacent to exactly one vertex that's been colored. So how many possible colors could we color this vertex here on the right? K minus 1. And the one remaining vertex, how many colors could we color this one remaining vertex? Again, it's the K minus 1. So if we put this all together, notice what happens. That first graph is K times K minus 1 cubed, and then we have that extra factor of K from the singleton. Okay? So you put it down, or I shouldn't say you put it down, you multiply these guys all together. I'm going to combine the K, so you'll get K squared times K minus 1 cubed, and bam, you get the same exact chromatic polynomial. Notice there's a reason I went ahead and did both of these two examples. Chromatic polynomials are not unique. In other words, what? You can totally here have two different graphs with the exact same chromatic polynomial. Yes, and the chromatic number for both of these guys would be 2. And 2 being the smallest value for K that you could plug in and not get back an answer of 0. All right. So that takes care of that and that question. The next couple of questions that I've got for us are finding the chromatic polynomials of some of the standard, or I shouldn't say standard. We did the example of finding the chromatic polynomial for path. Then we're going to do it for the complete graph. And then we're going to look at trees. To be fair, that guy right there is considered a tree. So we'll define what a tree is and then talk about how you use this same technique on trees. And then we're going to see the real method of how you deal with graphs that are not trees. But you guys ask about that shortcut with polynomials. So let us do a quick aside and we'll talk about the shortcut with polynomials. And I'll go back up and put that quick aside up here. I'll put it to the side and then after class I'll move it in so it lines up fine. All right, so here's the quick aside. If you have a minus b raised to the n, and actually this works with positive too, so I'll just go ahead and put a little positive here. Here's how it works. Okay. First of all, you use Pascal's triangle. So Pascal's A. Pascal's triangle looks like this. I'm assuming you've all seen it, even if you don't remember the name or were never told the name. You got a 1 up top, and then 2 1s all on either side. Nobody's lined up and down, no vertical alignments. Then you have 1 2 1, then 1 3 3 1. Anybody spot or remember the pattern? Anybody got a guess what the next row would be? Yep, so the next row would be 1 4 6 4 1, and it keeps going. The key thing here is the outermost parts are all 1s. The innermost guys are 1 2 3 4. The count here is which row you're on. So this guy here is row 4. That guy is row 3, and the very, very top row up here is considered row 0. Okay. So one number in is the n, and then all of the middle numbers are what? It's just going to be adding the 2 numbers that are above it. So if we did our next row, n equals 5, and that's going to be the last one I do because I ran out of space. What happens? We'll have our 1, our 5, and then you add them and get your 10 and 10. So notice here the 10 was 4 plus 6. 4 plus 6. You've got your 5, and actually notice those also keep the same pattern. And lastly, you've got the 1s. So really the thing that you have to remember is when you build your new row, you start and end with 1, and all the numbers between the starting and finishing 1 are going to be the sum of the 2 numbers above you. Okay? And notice this is why these numbers are offset, because that way you can easily spot the 2 numbers above you. These guys are your coefficients. Okay? So what you do is each term in here is going to be a raised to some power times b raised to some power, and the sum of those 2 exponents has to, that was so trying to be a k. Sorry about that, it looks like an x. The sum of those 2 exponents has to always add up to 1. Okay? Yes, so the next line would be the 1, the 6, 15, 20, 15, 6, 1. I'm going to write down though. So each term looks like this, and the coefficient in front comes from Pascal's triangle. Specifically, it's the row that corresponds to n. so the exponent that you have. So looking at the expanded polynomial I had, we had over here k minus 1 to the 4th. This guy was going to be what? It was going to be, we're going to look at row 4. So let me highlight row 4. So the very, very first coefficient was going to be a 1. Then we were going to multiply by k to the 4th times negative 1 to the 0th power. Notice the 4 and the 0 add together to have that exponent of 4. Okay. Next term, the coefficient is the 4. Then it's k cubed. Then negative 1 to the 1st power. Notice the exponents add together to be 1. And you do want to have the k here be decreasing, so 4 first all the way down to what it could be. Next, we have a coefficient of 6. Notice 6 is the next one in the row. You've got here k squared. Then negative 1 raised to what exponent? 2, perfect. Then our coefficient is 4. We have k to the 1st power and negative 1 to the 3rd power. And then our last term is 1 times k to the 0th power and negative 1 to the 4th power. When you simplify, this is exactly the same as k to the 4th. Notice the negative 1 here is going to alternate in sign all the way through. So this is negative 1 4k cubed plus 6k squared minus 4k plus 1. If you have k minus 1, what will happen is it will be k to the 4th all the way down to a constant term. The negative 1 will cause all the signs to alternate, and your coefficients are exactly those rows right there. Now, if we had been subtract 2, the 2's inside of here, instead of being negative 1s that only make you alternate in sign, the negative 2's would actually change up the coefficients. The 2's to the appropriate exponent would be multiplied by these standard coefficients right there. But if it's k minus 1 to an exponent, it's literally the coefficients or the rows from Pascal's triangle exactly, and you just alternate the signs. And since I've dealt with Pascal's triangle for way too long, I actually have the first couple of rows memorized, so I could do that really quick like what we did before. Okay. But that's the fast way of building out or expanding out, where you have something plus or minus something else raised to an exponent. Okay. That's also the way that I factored the other thing down here. This guy right here, notice the coefficients are 1, 3, 3, 1. It's alternating in sign, but the main numbers are 1, 3, 3, 1. That's 1, 3, 3, 1 right there. So I knew it was k minus 1 cubed, minus because the signs were alternating, k minus 1 here because the coefficients max exactly that coefficient. But Pascal's triangle is really awesome because a lot of our terms that we're going to see in these type of chromatic polynomials are going to be k minus 1 raised to an exponent, and you can actually just pull them really quickly out of Pascal's triangle. That way you don't have to do all that algebra by hand. Okay? So hopefully that made a little bit more sense. I see no questions coming in from you guys whatsoever. So, questions? You're all good? All right, seeing no questions, I'm going to assume you guys are okay. So, we're going to move on to our next question, and our next example here is we want to build I actually want to build for you guys a formula for the chromatic polynomial of the complete graph. We didn't write down the formula for path graph, so let me go ahead and write that up here for you guys. If you have the chromatic polynomial for any path graph, it turns out to be k times k minus 1 raised to, and this n minus 1 is 1 less than the number of vertices. So with the complete graph, we're actually going to we'll look specifically at K5, but in general, we want to build the formula for any complete graph. So if we look at K5, we've got this guy, 5 vertices, and all of the vertices have to be adjacent to each other. So this guy looked, roughly speaking, like a pentagon, and then all the edges inside. So in other words, as many edges as humanly possible. All right, I think I got them all. All right, so for this guy, I don't want to label the vertices just because we're going to put those little k and k minus 1s on the vertices. But, well, All right, so if we go ahead and look at some specifications, we've got the number of vertices is 5, the number of edges, I believe the number of edges was supposed to be 10. The degree of all of these guys is 1 less than the number of vertices, so that's 4. And we know from previously that our chromatic number here is 5. Okay, so that's the details that we know already about our complete graph. Now, when we want to start building our chromatic polynomial, it turns out this is one of the graphs that we can use that same trick that we've done previously. So you pick your favorite vertex, doesn't matter, maybe you pick the one on top. So if we look at this guy right here, how many different colors could we potentially pick to go on this vertex? And remember, we're assuming that we have k colors. All right, so we could pick any of our k colors. Now, next you move to a vertex that's adjacent to a vertex you've colored. I'm just going to go around the outside of the circle. So if you look at this next vertex right here, how many potential colors could you color this vertex? Be k minus 1, perfect. Now, as we move around the circle, what's different about this next vertex? And I went ahead and circled it for us. Why k minus 2? You guys are correct, but any guesses why? Yeah, that is totally the key thing. That vertex that is circled, it's adjacent to both of the 2 vertices that we already had, so we can't use either of the 2 colors that were already in play. So if we were actually coloring this guy, we would have to pull out a new color. Now, if we then move on to the next vertex, and I'm going to go ahead and circle this one too, any guesses how many possible colors we could do for that vertex? Yep, this one would be k minus 3, minus 3 because we can't use any of the colors that we've used previously, so I'll go ahead and illustrate that with actually putting a color in. Now, here's the big guy, last vertex. Any guesses how many potential colors we could use to color that very, very last vertex? Yep, k minus 4 because you want to make sure it is not colored the same as any of those colors we've already used. Let's see how this one turns out. Ew. Oh well. Yeah. Now, if we put this all together and build our chromatic polynomial, notice what happens. This guy is k times k minus 1 times k minus 2 times k minus 3 times k minus 4. Does that look familiar to anybody? Maybe not the terms of the k minus something, but the procedure of what those numbers would look like once you plug in a value for k. Ooh, not what I thought you guys were going to say, but yeah, it does actually tie into something that you would see back from series. It is actually the format for a factorial. Now, it's a truncated factorial, which the official term for a truncated factorial is a falling factorial. But in terms of these guys, what happens is you keep going until what? You get to the number of vertices that you dealt with. So if we did this in general, it turns out that the chromatic polynomial for any old complete graph starts with k, and then it's k minus 1, k minus 2, and you keep on going. And when do you stop? You stop when the number of factors, I can only go down that far. You stop when your number of factors is the same as your number of vertices. Well, if this is the complete graph on n vertices, this would mean you'd need n factors. Any guesses what you should subtract from k, or what should I write after k right here, as my factor got a little bit sideways there? There will be a minus n, but it turns out it's not actually just minus n, it's adjusted. Ooh, almost. So this term right here is k minus n minus 1, which means if you don't have the parentheses, what should it be? Yep. Now, here's the deal. No lies. I always had issues of saying, all right, do I need to add that 1 or subtract that 1? And it wasn't until I actually had to start teaching this that I remembered dealing with, that I had to start dealing with this bit right here, because nobody ever said it. So remember, when you're subtracting, if you do drop the parentheses, do the +1. If you keep the parentheses, keep the minus, okay? So the other way to remember is just keep going of subtracting a number until you get to the number of factors that equals exactly the number of vertices you have. So those are multiple ways to remember this one. The nice thing is, just like with a path graph, your complete graph, you can also use this exact same technique that we did before. Fair warning, I'm going to repeat this several times, but fair warning, this does not work in all graphs, okay? It only works on path graphs, complete graphs, and one other type of graph, of which our next example is one of those other type of graphs. So suppose you actually have this guy, and right after this next example, which is a graph of only singletons, in that particular case, what happens, any guesses what the chromatic polynomial would be for this guy when you only have singletons? Yes. So this one here, we call this guy of only singletons G, so this would simply be k to the 4th. Why? Because each one of these singleton guys, it does not matter which color you use. Yes, so in general, if you have a bunch of singletons, it doesn't matter how many you have. It turns out your singleton graph is the only graph where you actually have what? You actually just have a power of k, so k to the nth power. Now, why would that be true? Because notice here, if we went back to our properties of chromatic polynomials, this is exactly the same thing as k to the 4th plus 0 times k cubed, all of these guys 0. This tells you right here that you have what? You have no edges in your graph, or smallest visible term in the polynomial. This tells you you have 4 components in your graph, okay? So remember how we said previously, typically there wasn't a unique chromatic polynomial for a graph? Well, that's normally true, except in the case where you have only singletons. In that case, that's the only time you would get this k to the nth power, okay? All right, so we've had a couple of examples of the third type of graph where we can use this technique, where we just check to see how many different colors could be on each vertex. The 3 types of graphs where you can use that technique are paths, which are actually a special case of the third thing, the definition we're about to have, and complete graphs. And now let's get that definition. So the definition that we're going to care about is a tree, and there's actually 2 ways to define a tree. I don't care which one you decide you want to memorize or if you write them both down. So formally, a tree is a connected graph with no circuits. Or you could also say this, it's a graph where there exists between any 2 pair of vertices in your graph exactly 1 path between those 2 vertices. Or, please note what this means. There's only 1 face. So trees are always planar. So that means they have faces. And the only face in this graph is the unbounded face. So there's no bounded faces because there's no circuits. And remember, our bounded faces, we're dealing with circuits. Now, why are they called trees? Here's an example. So suppose you have somebody that looks like, oh, I don't know, this guy. Maybe you have a vertex. Maybe you go out somewhere. Maybe you go down somewhere. Maybe this guy's also sort of down. This guy's out. This guy's sort of up. You go over here. You go. So this would be an example of a tree. Notice what's going on here. It literally looks like, well, if maybe you rearranged it a little bit, it kind of looks like a scraggly bush or an actual tree that you might see outside. Yes, those names happen a lot in graphs. Okay? Notice, though, you have no circuits, so you have no bounded bases. It literally kind of, I don't know, it kind of looks like a squid-type shape, except there's no body for the thing. Okay? But that would be what a tree would be officially, no circuits whatsoever. Or if you prefer, pick any 2 vertices you like. there is exactly one way to get between them. There's one path to get between those two vertices. Okay, those are the two different ways. Why? Because if there was a second way to get there, you'd automatically have formed a circuit. For example, that dotted line, if it had been in there, you automatically would have formed a little subcircuit, or you would have had two ways to get between these paths, or you would have actually had a bounded face. Okay? So that's the idea behind a tree. Questions? Make sense? Kind of feeling okay-ish. Ish there being the key word. All right, so that's the example of the tree. Trees are the last situation or the only other type of graphs other than complete graphs where you can use the trick we've been using to build your chromatic polynomial. So if we use the trick that we've been using, oh, good, I have space. So let me just get rid of that guy and we will draw this second example below here, right there. So suppose we have this other tree, and I'm going to get rid of the extra markings right here. Okay, so here, maybe you have a tree like this. Oh, not red. Oh, well, we'll go with red. Bam, another tree. Okay. So what happens with this guy, if we wanted to find the chromatic polynomial of this particular tree, what could we do? Well, you would go through it strategically the same sort of way that we've been doing, finding our chromatic polynomial for all of today, okay, and the very end of last time. You pick your favorite vertex. It doesn't matter which vertex you do. Previously, we picked a vertex with the highest degree, which is totally fine to do. Let's be sort of obstinate and contrary. Let's pick a vertex that's on the far side, but maybe we pick on this vertex right here. If we tried to build the chromatic polynomial of this particular tree, how many different ways could you color the circled vertex right there? Yeah, same method as before. You could pick K different colors. Now, for the next one that's adjacent to this guy, how many different colors could you pick to color this next adjacent vertex? Don't overthink it. So this one here, you've already used up one color. So this means you could use any of your K colors except the one you've already used. So K minus 1. Now, when we move through the graph, notice you're strategically going along with vertices that are adjacent to vertices already colored. So these two have now been colored. We have to move on to this vertex of degree 4. So how many different colors are currently available to color this degree 4 vertex? Be K minus 1, because the only color it's not allowed to use is this one we already had. So here, maybe this one was colored yellow. This one could be colored yellow again, but the other previous one had to be colored some other color. Now at this stage, we actually have 3 possibilities where we could go, and it really doesn't matter which one we go to. But maybe we go to this one that's way up top. So how many colors could we potentially color this guy way up at the top here? Exactly. So the remaining 3 will actually all could be colored with K minus 1 different colors. Why? Because they are all degree 1. They're all touching or adjacent to exactly that one vertex right there that was colored in what? Colored in yellow. Okay. So maybe we do something like this, and that would actually give you the minimal coloring or the chromatic number. But if we put together a chromatic polynomial, notice there's only one copy of K. All of the rest of the vertices there could have been colored with K minus 1 possible colors. We just have to count up how many of them. Looks like there's 5 of them, so this guy would look like that. So notice here in terms of what we did, that's the same sort of format that we got for our path graph. When we looked at that disconnected graph, that one of the components was a star graph, we got the same format. It turns out that if you find the formula for a tree in general, did I flip-flop these guys? Yeah, I totally flip-flopped these guys. Let me go ahead and show you the formula and we'll come back to this. The formula is this thing right here. Your trees, any tree you have is always going to be one factor of k, and all the other factors are k minus 1. And I went ahead and wrote in the formula for the complete graph there as well. Okay? So we just built up to these two formulas, which in your book is in Theorem 5. They're going to go back and do a couple more properties of trees, and then we're actually going to use this stuff. So let's pick up a couple properties of trees. One of the properties of trees right here is if you have n vertices, the number of edges is, well, let's check it out. This one here had how many vertices? Did anybody happen to count the number of vertices for that example? I'm getting 6. Are you guys getting 6? All right, awesome. Anybody happen to count the number of edges? All right, yeah, I'm getting 5 too. Now, one graph does not give you a really clear idea of what's going on. So let's look at this other tree that was the previous example. Anybody spot how many vertices were in that past example? And we'll also grab the number of edges here too. Is it 9? 1, 2, 3, 4, 5, 6. Yep, totally 9. Anybody spot how many edges? Yep, it does turn out to be 8. Anybody notice a pattern? I realize with two graphs, a pattern is not established, but anybody have a hypothesis on the relationship between the number of vertices and the number of edges on each tree? It is. It does turn out the number of edges in your tree is always one less than the number of vertices. That's the same relation that you have in a path. A path graph is actually a special type of tree. Star graph that we've had previously is also a special type of tree, and they have the same relationship. Okay? Just as a heads up, those are some things that happen with trees. And when we jump into Chapter 3 is all about different things you can do with trees. Why? Because they're super duper important. We see them everywhere, both in math and computer sciences, where they're really big. Okay. Now, the other thing that we have that's important with trees is a related thing called a forest. Don't overthink the naming convention here. It is semi-descriptive. I'm sure somebody had a real chuckle when they named it ages ago. A forest is a disconnected graph where all the components are trees. Again, like I said, don't overthink this. That's it. That's all a forest is. Okay. Now, here is the theorem we've actually used earlier today. If you have a disconnected graph, and there are very, very, very few theorems about disconnected graphs. If you have a disconnected graph, and the components of the disconnected graph are, I labeled them with H's. So H1, H2, H3, however many of them you actually have. What happens then, what do you do to find the chromatic polynomial of the disconnected graph? You find the chromatic polynomial of all the individual pieces, and this is true regardless of whether you have a forest, which has a bunch of components that are trees, or if you have a disconnected graph that's not a forest, and maybe some of the components are trees and some of them are not. What do? You find the chromatic polynomial of each component and then multiply them together. And that's it. So that's the theorem, the property that we used earlier. All right. So that gets us into two really huge properties, both of which we built up to. Now let's actually get to some definitions, because we need these definitions for the theorem we're actually going to use for everything that's not a tree and not a complete graph. All right, so there are three graphs that are built from or related to your original graph G. One of them is this guy right here. The symbols that your book uses is capital G to indicate which graph you start from. And in the subscript, he does a little plus, and then this little ordered pair XY. Here's what it means. It means you literally started with a graph G and you added in the edge XY. So added edge XY to graph G. Okay. Now, let's look at an example to see what that actually means. And we'll get down here to all three of them. So the example is, and let me go ahead and make this a different color so it stands out. I made a super, super baby graph. I'm just going to do a little 4-cycle graph. So suppose G is this guy here. It looks like a little square. And I'll go ahead and pick on two vertices that don't currently have an edge between them. Maybe that's X and that's Y. If that's the case, your graph where you added an edge in would literally be the same graph you started with in G, but now include the extra edge between X and Y. That's it. By far of these three graphs, that's the easiest one to do. However, please be warned, this is the one that we're going to use the least. Terrible, isn't it? Actually, let me put a little bit more space between these guys. All right. So next up is same symbol, except now there's a little minus in between. Any guesses what you would do here with this graph? Hint, it's something with respect to our edge X, Y, and graph G. You got it. So we are going to remove or delete this edge X, Y from, oh, I just messed up the word from. There's no way to recover that. So from graph G. Okay. So using the exact same little baby example, suppose we've got our graph G, that's that cycle graph. It's got 4 vertices. But I'm going to pick a different 2 vertices, X and Y. Why? Because in this case, you have to have the edge X, Y in the graph to start with. So you pick 2 vertices that form an edge. I'll be lazy and do ones here that on that side. So when you go ahead and you remove that edge, again, don't overthink it. We're literally just going to remove the edge. The vertices have to stay because notice these vertices are in fact endpoints of those other edges. And let me go ahead and put some extra space in this one too. It looked like I didn't allow enough space for these examples. Now, the last one is actually a little bit different. This one's a little bit more complicated. And just as a heads up, this guy that we just did also has the symbols G and then a step subtraction symbol, a slash, and then E, where E is the name of your edge. So if you're looking this up online, it has this symbol too, which honestly is a little bit more common than that symbol. Now this last one down here that your book has, it's a G. Again, we're going to start with graph G. And this one here is sort of a weird subscript. It looks like where you says X equals Y. And this one, your book uses the word coalesce. It is more common to use the word edge contraction is what we're actually going to do. Okay? So let me write down the word your book uses because this is something that you see around. Making sure I can spell coalesce. Let's really hope I copied down the right spelling the first time, which I have to admit, I hate the word coalesce. In my head, I always think of merge instead. So we're going to merge the vertices X and Y together where X and Y are vertices. Okay? I know. So this one here, the actual thing that people say, this is called an edge contraction. So I have to admit, though, even though that is the standard, that one doesn't seem a whole lot better. All right, so here's what you see. Starting with the exact same graph. So again, we have this same cycle graph that looks like a square. So here's our G. I'm actually going to pick on the same 2 vertices we did in the last example, and that is strategic because in the future when we use this, you do normally use these 2 guys together, and you're going to pick on the same pair of vertices when you build the 2 different new graphs. So let me highlight here. So that's the edge we're really picking on. Okay? So when you do the edge contraction, or you merge your 2 vertices, and let me do the symbols. I have to admit, I normally forget to do the parentheses, and really your book's one of the few places that actually shows those parentheses. What you will have is you keep your original edges, so let me name these edges vertices A and B. The vertices X and Y now become the exact same vertex X and Y, and then you put in all the edges. So your edge AB is still in there. Your edge AX is still in there. Your edge BY is still in there. And the edge that you picked on, it's going to disappear. It's not going to turn into a loop. So yes, this guy does turn into a triangle. Okay? Now, here's why we care about these guys. It turns out these three graphs we use to build our chromatic polynomial. Okay? So there are two formulas. Your book does give you two formulas. Because one of them is the actual theorem and one of them as a corollary. And I don't know why your book put them in this particular order, because it's exactly opposite of every other sane human being in the world. Okay? The one that is actually used is the corollary. So that's the one that I'm going to go over with us, mainly because I really hate the other one too. So Theorem 6 says you take your original graph, you pick any two non-adjacent vertices, this is key non-adjacent, and you build two graphs, the one where you do an edge contraction, that one's finally not adjacent, and then in the other one, you go ahead and you add in an edge, and then you calculate the chromatic polynomials of those two new graphs, add the two chromatic polynomials together, and you get the chromatic polynomial for your original graph. Okay? We're not going to use that one. Here's the one we're actually going to use. We're going to use the corollary. So here what you do is you go ahead and you grab two vertices, x and y, and I totally did a typo here. Just a second. I was like, wait a second, that's not going to work. In the corollary, you pick two vertices, and here the key thing is they do have to be adjacent vertices. One of the reasons I picked on adjacent vertices right up here in the graph. And there's two things you do. You build the last two graphs we had. The first one is you remove the edge that's between those two adjacent vertices. And the other one is you do the edge contraction on that edge that you had. Okay? To be fair, even though I laughed a little bit at the book of his word coalesce, the buzzword here of edge contraction really only applies to the situation where you actually have your two vertices adjacent to each other. If you picked on two vertices that were not adjacent to each other, it wouldn't actually be an edge contraction. You'd be having to merge those two vertices together and look slightly different. Okay. Now, in this case, when you remove your vertex and you remove your edge and you do your edge contraction, you subtract the two resulting chromatic polynomials to get the chromatic polynomial of the original graph. Okay? So this is the formula that we're going to use. And what we're going to do is we're going to apply it to a cycle graph, specifically that same little example that we did for the three types of building where we added an edge, removed an edge, or did the edge contraction. Okay? This is a situation where you cannot use that same strategy that we did last with all our other examples where you just say k, k minus 1, etc. Even though it feels like it's going to work, it turns out it doesn't. It doesn't give you the right numbers. Okay? So here's what you do. Personally, I find it easiest if you actually build a decision tree as you're going along. In other words, a flow chart. Okay? So first thing that you do is you pick on two vertices. They have to be adjacent. It does not matter which two vertices you pick on. So because my hand is here on the right side because I'm right-handed, I'm going to go ahead and just pick on vertices B and C. You don't have to pick on those two guys. You just have to pick on two vertices that are actually adjacent to each other. Okay? Then what we're going to do is we're going to do two things. We're going to build two graphs. One of the graphs that we're going to build is where we're going to subtract the edge BC. So we'll build the graph where you subtract BC. And then we're going to edge contract BC. In other words, we're going to merge the two vertices B and C. And we'll come back to that formula in a little bit. Okay? So this one here where you just remove the edge, no worries. That one's easy to see. It looks like this guy. Bam. Now notice this is what? This is actually a path graph. So since there are no circuits, it's a path. In other words, it's a tree. We actually know what the chromatic polynomial is for a tree. What's the chromatic polynomial for a tree? Yeah, it's going to be k times k minus 1 raised to 1 less than the number of vertices that you have, so in our case, 3. Okay? So notice we could totally have labeled this with little itty-bitty, teeny-weeny k, k minus 1, k minus 1, k minus 1. When you get to the point where you have a tree or a complete graph, you stop and you use the formulas that we've already talked about, which is why now the other one over here, we did this example just a second ago too, so let me go ahead and draw in what that graph is. When you merge the two vertices together, you still have your vertex A, your vertex D, but now you have the combined vertex of B and C, so you're going to get that triangular shape. Now, quick check. This triangular shape is most definitely not a tree because you've got a bounded face right here. You've got a cycle involved or a circuit involved. In this particular case, though, I'm going to claim that it is a complete graph. Which complete graph is it? Yep, it's totally K3. So you can pull out the formula for K3. You could always do it again, and we'll have to on more complicated examples, but if you have a complete graph or a tree, please save yourself a little bit of work and me a lot of reading and actually just do the formulas for those guys. So in this case, anybody remember what the formula or the chromatic polynomial would be for K3? Anybody remember this guy? I may have totally given it away, although I think you were typing it at the same time I was writing it. Yep. So this is the one where you have k, then k minus 1, and you keep decreasing all the way down until you get the same number of factors as number of these, in this case, 3. Okay? Now, put this together. This is where we need our formula. Our formula says, so now that we have actual chromatic polynomials in both cases, this tells us that our chromatic polynomial for our given graph, C4, is the chromatic polynomial of, and I'm going to go ahead and use the label right here of P4, although you don't have to. Subtract the chromatic polynomial of the complete graph K3, but what you actually do is you drop in the actual chromatic polynomials. So this is k times k minus 3 minus k times k minus 1 times k minus 2. Please note that is a perfectly fine way to stop if you don't want to keep working. However, notice what we saw earlier. If you've got, with all the pieces and parts that we know about the chromatic polynomial, having it in that expanded form is super helpful. The other way of this particular guy is actually having it in factored form. So the two really, really useful formats, factored form and then just expanded all the way out. No lies, if you write it expanded all the way out, it's easiest for me to grade because there's only one polynomial you'll get. Factored form, sometimes there's multiple ways that you can get it. Okay. In this particular case, if you wanted to actually factor it, because I ended up not actually writing this thing out and expanding it, so I can't just write it out for you here. Factored form would be, what is that? That first one is an extra copy of k minus 1 squared. And this one over here would be what? Minus a k minus 2. I forgot the parentheses. So this is k minus times k minus 1. What is this? K squared. That would be a negative 2k, so a negative k. The positive 1 plus 3. That might be a factored form if you like, okay? Or if you expand it out, I see that one of you did that, so when I write out that expanded form, I'm going to assume that you did it correctly. So minus 4k cubed plus 6k squared minus 3k. Quick check. We had 4 vertices, 4 edges, and 1 component. Looks good at first glance in alternating signs. Okay? So this is the real way that you deal with finding chromatic polynomials of graphs. Okay? We've run out of time. Next time we'll start off with another example. It'll actually be this example right here that'll be a little bit bigger. And that was actually my last example that I planned on doing with chromatic polynomials. But notice here, the key thing is very much do a deletion of an edge and then do an edge contraction and plug it into that formula. Okay? Yes, recursive or recursion can totally happen and often does with more complicated examples. This is not a complicated example. All right, but that's it for today. I'll hang out for a little bit if anybody's got any questions, but we're done. That's it for today.